Hello, it's Ryan. This is another video on a different phenomenon of light known as the Doppler effect. The Doppler effect is used both in sound and light phenomena. You've definitely heard the Doppler effect in your car as you drive, or as someone drives by you while you're not in a car, or as a truck drives by blaring its horn. I'm sure you can imagine the frequency of the sound that you're hearing changing depending on if the truck is moving toward or away from you. The same thing happens with any sort of wave and relative motion. It's called the Doppler effect. So we're going to just remind you that the Doppler effect is the apparent stretching or compressing of a wave, of an EM wave, relative to the motion of an observer and an emitter. So we'll say the apparent stretching or compressing of an electromagnetic wave for an observer relative to a moving emitter. And so one example might be, so we could say diagrammatically, you might have like a tower, and it would be a really annoying tower if it was just emitting pulses of light for no reason. Let's say it would be yellow light. And maybe that the observer will be in a car that can drive really, really fast. And so the observer would see, if the observer, V observer, is 0, then the observer would see yellow light. So this is, we could even have it be yellow. And so our observer, well, we can make him a big eyeball if we want, would be seeing whatever wavelength yellow is incoming from the source. Now, if we could drive close to the speed of light at an instant, we'll talk about that in another lecture, very fast, V car, or observer, is fast, and it's moving toward the light source. Now, the yellow light waves that are hitting the observer, if we're moving fast enough, will seem compressed, meaning they will look like they have shorter wavelengths. Shorter wavelength than yellow, Roy G, BIV, would be green. And so our observer, having the big giant eye that they have, would see those yellow waves being compressed with shorter wavelengths, and they would see a green wave or a blue shift, meaning it shifted toward the blue end of the spectrum. In fact, why don't we just make him moving so fast that the light seems blue, just to really push. So we'll draw a much shorter wavelength because we're moving toward the emitted light. So we could note with V moving toward the emitter, we get a blue shift, which would be compressing wavelength, or shortening it. It's not really shortening it. The emitter is what's shortening it. The emitter is what's creating the light, but we are seeing a shorter wavelength due to our motion relative to the emitter. Now, if we were to drive backward just as fast, V observer, very fast. Now, instead of compressing the wave, we would be seeing the wave get stretched out. It would be longer, which would be a redder wave. And so now the wavelength would look longer, and it would appear redder, or red shifted. would appear stretched out. Now, it's important to always remember that the emitter is emitting yellow light in this case, and so the emitted light never changes wavelength. It would just be what we observe depending on our velocity. Now, what you're all really interested in, I'm sure, would be the mathematical representation of all this. And mathematically, it's a nice straightforward equation. We have the frequency of the observer, so the observed frequency is equal to the transmitted, or we could say emitted frequency, but I like to do an S for source, the source of the light, and it's multiplied by 1 plus or minus V relative over C, and it's definitely worth noting what these are. So we'll say F sub O is our observed frequency. We know that Fs is our source frequency, but we could also note that that's just the emitted frequency. So either way, we also know VREL is V relative, but not V relativity. So be careful. This is the relative velocity of the, we'll say actually between the observer and emitter, because really either one could be moving. So we'll say between the observer and emitter, or observer and source. We know that if F sub O is greater than Fs, then that they will be coming together, which means, of course, we would be using the positive. And if the source has a greater frequency than what is observed, then we know that they would be separating or moving away from each other. And if they're separating, then of course, we know we would use the minus. And so that is the Doppler effect mathematically. We might as well just do an example here. So in this example, this is a Doppler effect example. And in this example, we're going to say that there's a probe orbiting Pluto. So we'll say the probe orbiting Pluto is moving toward and away from Earth at various times, of course. Does anyone know how far away Pluto is from Earth? I'll tell you that it's about 40 AUs from the sun, so on average it's probably about 40 AUs from us. Anyway, the probe is orbiting Pluto and it's moving toward and away from Earth at various times. We know that the source frequency is a gigahertz. We know that F source is 1 gigahertz, which is 1 billion hertz. And we want to determine, so we know that, so let's determine the observed frequency, F sub O, the observed frequency at 4 different points as shown. So that's what we're going to do. So we'll have Earth over here. Here it is. Earth. We'll have Pluto, and none of this will be to scale. Way over here, there's Pluto, and there's going to be our orbiter orbiting Pluto, and we're going to show 4 spots. So this is Pluto. And we know that at these 4 spots that it's making this nice circular orbit around Pluto. It has velocities like so. We also know that V in general, the magnitude of the source, is equal to 23 kilometers per second, which is approximately 51,000 miles per hour, in case you were wondering. It's really cruising along. We're assuming Earth is stationary at this point. And so what we need to do is figure out the observed frequency at 1, 2, 3, and 4. So we know that in general, f sub o, the observed frequency, is equal to, and we'll have fs, which we know, 1 plus or minus, depending if it's moving toward or away, v relative over the speed of light, c. We could also note that 1 AU is an astronomical unit. This is 40 AUs. It's actually 39 and a half about on average, but we like 40, it's easy. 40 AUs. 1 AU is an astronomical unit. It's the average distance Earth is from the sun. And it's, of course, equal to 1.50 times 10 to the 11 meters, or if you want to be really specific, you could give exactly what it is, and I believe it's 149,597,670,700 meters. I hope I got that right. It's been a while, but there it is. We'll just use this for funsies. So to solve this problem, we're looking at the 4 spots. Our first spot is here, and our first spot is the probe, which is moving down the page. Is it moving toward or away from Earth? And at that instant, I don't think it is. So we know V relative is 0. See picture. And if V relative is 0, then we would get F sub o equals Fs, 1 plus or minus 0 over C, which is just Fs. And so F sub o equals Fs. I bet that would be the same for spot 3, wouldn't it? So we can note spot 3, F sub o equals Fs, since V relative is 0. Remember, if V relative is moving toward or away from Earth, we have something, but if it's moving in a direction that is neither toward or away, then it would be not moving toward or away. I think that sounds redundant, but it's the way it works. Number 2, we have this one. Number 2 has a velocity moving away from Earth. Now, if we remember from our definition, if it's separating, we have a negative sign. And so we know for V relative, in this case, it will be negative 23,000 meters per second. And so our F sub o equals Fs, 1 minus 23,000 meters per second over the speed of light. And if we calculate this, we'll end up getting F sub o equals 0.99992 gigahertz. And so it's not much different, but it is different. Our final spot, number 4, now the velocity is moving toward the Earth. As you can see, velocity is moving toward the Earth. And so we'll just use the plus instead of the minus. We'll know that the wavelength will be compressed, and so the frequency will go up and the wavelength will be shorter. So we have F sub o equals Fs 1 plus 23,000 meters per second over 299,792,458. You're always welcome instead of using this actual speed of light, to just use 3.00 times 10 to the 8 meters per second. That'll do just fine. And we'll get 1.123477 gigahertz for our final answer. So that's a quick example using the Doppler effect. I hope that this was easy to watch, and I'll talk to you soon.